Okay, so talking again about log Calabi-Yau. So this is some log Calabi-Yau. And in particular, we have its tropical set. Trop-R. And you can think of this thing, this is not entirely true, but think of it, you can at least think, it's homomorphic to Rn. In general, in complete generality, it has topology very similar. It's a Q homology Rn by a theorem of Kolar. But in the cluster case, for example, it's homomorphic to Rn. And as I was talking about last time, and as Mark explained, so inside of this thing, so this is just a piecewise linear. You know, Paul would stress this. It's just piecewise linear. We don't know what straight means in this thing. There's no notion of straight in here. But what there is there are a distinguished collection of paths. There's just a canonical collection of piecewise straight paths that we're calling broken lines. Broken lines. So these are some paths. These are some distinguished paths. Paths. What are they? The way I'm thinking about them is they just, each of the straight bits has a vector attached to it, which is parallel to the path. We have these vectors and it has some base point here. I'll call these things gamma. That's what I'll call a broken line. And this part, the one end, this is infinite. This goes off to infinity. This is supposed to, last time I talked a little bit about why there should be this distinguished collection of paths in the Berkovich world. This thing is representing the tropicalization of, so there is a zero in this world. There are rays in this world. It makes sense to scale in this manifold. So here we have some direction P. So this is going off to infinity parallel to P. What does P correspond to? That corresponds to some boundary divisor, some EP. This is a divisor at infinity. So we have some compactification here of now a picture of U with some boundary divisor, partial compactification. Here's U inside some compactification, partial compactification, let's say Z, which is just U union, just this E, this one divisor. There's EP. Though maybe I should draw it down here. Let's draw EP here. And what this is supposed to be the tropicalization of is some version of a disk here, a rigid disk in the language of before, which is mapping down to here. So it's a kind of half-infinite cylinder in this picture. But then there's a point at infinity. That's what's touching there's one point of contact with the boundary. So that's where the broken lines come from. And the thing, all I really need for the part of the lecture I'm going to talk about today, you could have just blow off, as many of you were forced to do, that discussion before. The real thing that you really just need today is the existence of these broken lines. And if I fix some now compactification, I don't actually need this to be a minimal model or anything, just a compactification, and a curve class. Just a curve class, just a class of a homology class. So this, if you remember this, the Mori cone that just lives in H2YZ. Then we get a number, and gamma, and a broken line. Then we can count them. So we get a number M. We can count M gamma in the class C. That is some number, some integer. So we count these. Well, we count. We as I explained, this is rigorously done. We count these disks. The way Mark was introducing broken lines, the number just comes with it. That's the coefficient, the coefficient known in front of the monomial that he was attaching to each segment of the broken line. So that's just the Mark's thing. Mark's formulation. There's just an integer that comes with this last piece here. That's this integer. Once we have these broken lines, I can actually now give you the structure constants for the multiplication rule. So C is a curve class. So just you give yourself a class of a curve in this compactification, and then you count broken lines in this class. There's a little subtlety here, as I mentioned it. If I have time at the end, I'll go back to the Berkovich space. Here I have an open, this is a disk. Where am I getting a curve class? How come I getting a curve class? But remember, I was saying that the boundary of this disk lives on the fiber of the SYZ fibration, and there was this. Well, let's just skip it. It's a. You don't see C is. let's see, I'll explain it to you afterwards where this C, but you fix a curve class to make this count. In, roughly, I could say in some formulation, you could imagine this. No, let me just leave it out. It's a bit subtle to get the class of a closed curve from an open curve. And I gave an explanation in the Berkovich world last time where that would come from. Excuse me? Yeah, I'm not worried about torsion. You mean in H2 of YZ? I would just take a class in the in H2 of YZ. If there's torsion there, that's fine for the count. Okay, so let me give you the structure constants now. So recall we had this algebra A, which was we had a free module that we're trying to make into an algebra. It's just this direct sum over Q and U trop Z of what I called R before, R theta Q, and what was R? This was the direct sum over all the curve classes of just the coefficients. I'll put Q. I could really put Z here, but it won't look good because I'm writing this formal variable, Z to the C. So this is this is as a Q vector space. This has a basis with which are products of these thetas and these guys. These guys are easy multiplications. So Z C1, Z C2, two curve classes. You just add them. These are just ordinary monomials. So we want an R algebra structure on here. I want an R algebra. So what I have to do is I have to tell you if I take theta P1 times theta P2, I have to tell you what's the coefficient of Z to the C theta R. So that's what we call, this will be the sum of over R and C of, we'll call it alpha P1, P2, R, C, this, C, Z to the C, theta R. So you give me, you give me P1, P2, R, those are three tropical points and a curve class, and I'm supposed to give you a number. And what we do is, this might look a little strange, but bear with me. We count pictures that look like this. So here's a picture of the tropical set. Z trop. I've got 0 in there. I've got let's say P2 and P1. I got the ray spanned by P2, the ray spanned by P1, and then I have a point R. And I pick a base point B close by. So B is a point close to R, and we'll get pictures that look like this. Let's just have this continue. The whole blackboard is the tropical set. It's going off like this. This is going off. Now, what's the meaning of this picture? So this is a broken line, gamma 1. Got one broken line there. This is another broken line, gamma 2, going out to here. What's true about it is this. So this is supposed to be parallel to this guy. His initial direction here is minus P2. His direction here is minus P1. And here we call that the final direction here of gamma 1. This one here, this vector, is the final direction of gamma 2. What we have is that they add up. This is required here in this picture, is minus R. So just to put it in symbols then, what's this thing? So alpha P1, P2, RC, it's the sum over pairs of broken lines, gamma 1, gamma 2, and then I'll have two curve classes, let's say alpha 1 and alpha 2. These are curve classes, N-E-Y. And what are the conditions here? That P1 plus, the things that I wrote there. So first, alpha 1 plus alpha 2 is they add up to the curve class C. The initial gamma I is minus pi. That's that's this thing here, and the thing I said about f, gamma 1, f gamma 2 is minus r. And what do we add up? We add up these counts. How many, roughly speaking, how many such pictures? So m alpha 1 gamma 1, m alpha 2 gamma 2. Okay, so that's this number. You can't see them. They're the class. They're the class of the holomorphic disk that this guy is the tropicalization of. So I fix a curve class, and you sort of break it up into sums of two other curve classes in as many ways as you can. And then for each one of those, find disks in those classes with these tropicalizations. So that's the definition of the multiplication rule, is by giving. So then we get. So the hard thing to show is to show that this gives an associative multiplication. This is the hard thing if you define the structure constants just directly by counts of curves. The hard thing is to prove that this is an associative multiplication. If you do it the way Mark was doing, then it's easy. What we actually show there is the way we actually do it in the paper is we build the space, the space that Mark was talking about using the scattering diagram. We build a space, and then we figure out what are the basis of functions on it. And so what's Mark was explaining that union of tori comes with theta functions on it. They're already there as functions. You just figure out what is the product of two of them, and you easily discover this rule from his point. So their associativity comes for free because they're already functions on something. Go ahead.
So these I've gamma 1 are the monomial associated to the...
That's right. In his formulation, that's the final thing.
Or it's
yeah.
the exponent, I think, with this formula. It's the exponent.
The exponent, yeah. Yeah, the m would be the coefficient in front of the monomial. He had some c times some formal variable to an exponent. The exponent is this thing, and the thing in front was the count. Okay. Now, all right, fine. Now let me say that roughly at this point, give me this formula, and just the idea that we have these broken lines just defined sort of even combinatorially. I want to show you that they have about half of our paper is the stuff that Mark talked about, and then the second half is where we get a bunch of applications. It actually just uses these things in a very simple way, which I want to talk about now. So you don't really have to have followed much. I want to talk about basically polytopes, convex polytopes in U-trop. Once I have these broken lines, I can define these. Why do I put these in quotes? Because UT, this is the U-trop. Well, I just want to stress again that this thing convex polytope does not make sense in this thing at the moment. Because it only is a piecewise linear thing. As Paul did in one of his examples, he said, you take two tori in here, two copies of the torus, two different copies of the torus, that identifies the tropical set with the vector space R in two different ways. And Paul had one example here. He had a picture that looked like this, if you remember. Then he had this piecewise linear map. Went like this. So it was identity over here on this half of the world, and on this half of the world it was a simple shear. So notice, for example, this set here is convex, but when I apply the piecewise linear isomorphism, it becomes this thing, which is not convex. So convex is not preserved by piecewise linear maps. There's no notion of convex at the moment. But we can use broken lines to define it. And once I know what convex means, then I'll know what a convex polytope is. So here's just an easy lemma, an easy fact. Suppose I've got a function from Rn to R, which is piecewise linear. Piecewise linear. What does that mean? In other words, I've got some fan. I've got a bunch of cones in Rn broke up into cones, and on each one I have a linear function. And they agree. They agree on the walls. So you get this is a continuous function. It's linear on each of these cones. And the statement is that f is what I call min convex, meaning the minimum of linears. In which case it will be the minimum of these linears. So we're saying that f is just the minimum of all these guys. If and only if the derivative of f evaluated on V is non-increasing along a straight line, along any straight line, let's say generic straight line. You can test it by, so what I just mean, take a straight line and take a constant tangent vector along it. Then the L, you take L applied to it, this L applied to it, this guy, that should be non-increasing. That's a triviality to prove this thing. So What does min convex mean? What does it mean in terms of the graph? It means the graph looks like a tent. It goes down as you go around. So now what can we do in U trop? Well, I can just use this as the definition. So now suppose I've got a function from U trop to R, which is piecewise linear. I know what piecewise linear means because the mutations are piecewise linear. So if this is piecewise linear, I'll just define, I'll say it's in quotes, min convex, if the derivative of f evaluated on each of these vi's is the same thing, non-increasing, along any broken line. Along any broken line. See what I mean? So the broken line has a bunch of these, has a vector along each straight segment, a parallel vector, and this is a piecewise linear function. I make that requirement, that it be decreasing as you go along. The remark, if we're in the cluster world, any line which is straight in some seed. So when I say, what do I mean when I say in some seed? I'll use this expression over and over. What I mean is this thing. You've got the U. You pick a torus inside of here that identifies U trop, becomes isomorphic now just with LR, just Rn. And then what I mean when I talk about, like I just said, if I have a path in here which is straight in some seed. So if I use the linear structure given by this identification for some seed and it happens to be straight, so straight in some seed definitely implies broken. What broken line means is there's a bunch of paths which we call broken, and we can in the cluster world we could define them in each seed, but the point is that they're preserved by mutation. And what I'm telling you is a straight line in some seed, that's a broken line. So what that implies is that if I take a function which is min convex, in my sense, that implies that it's convex, min convex, ordinary min convex in every seed. Do you understand what I mean? So do people follow what I'm saying? I've got this piecewise linear function. I've got a million different linear structures on this set. And I'm telling you this function, which is this piecewise linear function, will be convex in every one of those structures. This does not imply. This is a much stronger condition. It's hard to remain convex. I hope that example is showing it. It's hard to be convex simultaneously in all these different structures. But that's so that's my notion of what convex, piecewise linear convex means. And now I can define a convex cone. Convex cone. What's a convex cone? Well, I take the set. I take some f, which is min convex, and I look at the set of u in U trop, such that f of u is bigger than or equal to 0, which is the shorthand notation I'll use for that is just the set f greater than or equal to 0. So this is min convex. Again, this is a subset. This will be a convex cone. This will be a convex cone in every linear structure simultaneously. So it doesn't, even though some cones, like the one I drew here, they're convex in one and they lose their convexity in a different structure. These will never lose their convexity. So they're convex all the time. I can also define convex polytope. Convex polytope. Then I'll just, completely analogous, I'll just take f greater than or equal to c. Just take a constant, fix a constant, and look at this. And it'll be important for our discussions to know, when is this bounded? When is it bounded? When is this polytope bounded? So, in any linear structure in the cluster world, this will just be an ordinary convex polytope. I want to know, when is it bounded? Of course, if it's bounded in one, it'll be bounded in all of them. So it's bounded. That's easy to show. That's if and only if the function is actually always negative. F of u is less than 0 for all u not equal to 0. This is a simple thing if you have a min convex function. I'll use the notation just f less than 0. So if I get a bounded polytope inside of my space if I can find a min convex function which is everywhere negative. Okay. So now, what's the good of this? Why do I care about this? So let me go back to the Fock-Goncharov conjecture. So one thing that made this problem hard was that the conjecture, the Fock-Goncharov conjecture was, what was the Fock-Goncharov conjecture? Well, it said, for example, that atrop, that in this language, let's say that's our utrop, this parameterized a basis for OX, the X space. In the language here, there's O of the dual. This O of the dual guy. Well, so this is, what is this thing? This is just the lattice. This is just Z to the n, at least as a set. So this was impossible when we've thought about it a little bit. This is impossible because, or just false, because what does it say, roughly speaking? It says that all the X spaces of a given dimension have the same number of global functions. They have a basis parameterized by Z to the n. They have the same number of global functions. But many X have basically no global functions. Well, no interesting global functions. Interesting global functions. I know that's impossible to read. But what the X space comes with a map to a torus. I think it's the torus which is dual to the kernel of the skew form. It comes mapping to a torus for most X's that you write down. Like if you follow the description that Paul was describing. Take a toric variety, blow up a bunch of times on the boundary. Most of the X spaces you get will have no functions except for the ones coming from the torus. So this was just impossible. So the problem is, with the conjecture is that the X space doesn't have to have any functions on it. You need an assumption. So you need an assumption of the sort that X or A is affine. It's not literally affine because people who've played with this, these cluster varieties are unions of tori. They only sort of make sense up to codimension 2. So it's really kind of affine in codimension 2. But you need an assumption of the sort that these things have lots of functions. So where does our construction go wrong? Where does my algebra go wrong? So what's the problem in our construction? So in our construction, because so far, if you've been paying attention, or even if you have, it may not be obvious, I've never used the fact that my U is supposed to be an affine variety. I've not used it at all. Where do I get into trouble? The trouble that we get is we have this theta P1, theta P2 is a sum alpha P1, P2 R, theta R. I don't think I said this when I wrote the thing down. When we break it up into, maybe it's not up here anymore. This guy here, if I add up all these guys together, if I break it up into a sum over R's of a sum over C's. In other words, if I gather all the R bit, I'll write that as alpha P1, P2, little r, theta R. So this now lives in this group ring. It has this kind of guys. So we have this product. These make sense. We can always define this. This makes sense. But the problem is this, in general, this sum will be infinite. So the actual structure constants make sense, but when you multiply two things together, you get infinitely many terms. So in general, this is an infinite sum. And it will only converge adically at infinity. We have this in the paper. We call this the formal Fock-Goncharov. What's amazing is their conjecture is actually true in a very precise way at infinity all the time, which makes the conjecture even more impressive to me. So it's always true, but only in this adic way. It couldn't have been true because X doesn't have functions on it, but it does have these kind of formal functions at infinity. So when does it work? So when do we get a finite sum? I mean, the conjecture is the conjecture. When is it actually true? Then we better get a finite sum here. And I want to say that with these polytopes, it's easy to prove you get a nice condition for when it's true. Here's a little lemma, which is easy. Lemma. So suppose suppose that alpha P1, P2, R is not 0, and F is min convex. Then F at R is bigger than or equal to F at P1 plus F at P2. The proof of this would be like 3 lines long. it just comes from the definition of the multiplication rule, which I think I've just erased. But this, the multiplication rule counting pictures like this, this condition at the end and the definition of min convex. So this is like 3 lines long that this is true. So if we have, we have an f which is less than 0, then, this is constant. So when we take theta p1 times theta p2, as this in the sum, p1 and p2 are fixed. So this is fixed. Let's just call it C. That means that R lives in, this set fx bigger than or equal, or fu, just what I'm calling f, bigger than or equal to this constant. And this is a bounded polygon. This is a bounded lattice polygon. So I've got some bounded polygon here that's only determined by p1 and p2. This is f bigger than or equal to, well, f of p1 plus f of p2. And the r's have to lie in here. There's only finitely many lattice points in there. So we get the finiteness of this product just from this simple notion of convexity. So we get it for free. Now you might ask, well, where am I going to get such a thing? So what we're basically saying is if there is a bounded polygon, bounded convex polygon inside the tropical set, then I get a finite multiplication rule. I get polynomial multiplication. I can define this algebra. So how do I get min convex functions? Well, suppose I start with an ordinary function. From u to a, let's even a rational function. So I start with a rational function, non-zero rational function. I can tropicalize it and get a map from the tropical set to R. What's the map? So what's f trop? Well, a point of this is some valuation or some boundary divisor. What is it? Well, you just apply the valuation to the function. Or let's say f trop of a boundary divisor E is the order of, that's a divisor at infinity to our variety. We just take the order of 0 or pole of f along this boundary divisor. Go ahead.
Can you explain this number of how f is interacting with, where is f coming from?
So I'm saying you start, suppose I have any min convex function on the tropical set. And now, suppose I've got 3 points of the tropical set where this alpha is non-zero. What did that mean? It meant I had, broken lines of that sort coming down to R here at the end. I can draw broken lines like that of this thing where it starts with the direction P1 and P2. Then it's immediate, just from the definition of broken line, of the multiplication of, because you have this picture, just from the definition, you'll see that you have this inequality. So it means that R lives in this polygon. It's bounded, so I get the finiteness. So if I have a rational function, I can tropicalize it, and our conjecture is that if f is regular, then the tropicalization is min convex. Let me say that this is hard, and we couldn't prove it using the scattering diagram definition. But if we use the geometric definition of broken lines as coming from maps of analytic disks going into here, this is obvious. It just comes down to the tropicalization of the ordinary tropicalization of a Laurent polynomial in one variable. So certainly when we get the geometric definition of broken lines, this will just be immediate. At the moment in the paper we have it. If you look at our paper, we can prove this when f is a sum of global monomials, or say a sum of cluster variables. If f is in the upper cluster algebra, we have this property. Okay, so if f is regular, ft is min convex. And now when is ft negative always? Well, that just means that's equivalent to saying f has a pole on every boundary divisor E. That's in every possible partial compactification. I want to find a function which has a pole at infinity in all directions. It's easy to show that if U is affine, such an f exists. Such an f exists. For example, if you just take generators of the ring of functions and take their sum, we'll have this property. So affine, what I'm saying here is the Fock-Goncharov will be true if there exists, if U is affine. How do we see that? Let me just remark. In the cluster algebra, it's very hard to tell from the definition whether it's affine, because affine is not a local condition. Every variety is a bunch of affine things glued together. It's a little hard to tell the global thing, but Fock-Goncharov is true if U is affine, and the way we see it in convex geometry is kind of the analog of this is if there exists a bounded convex polytope. It turns into a kind of a curvature condition on the tropical set, that you can draw a convex polygon that's bounded. Yeah. Okay, so let me continue in this vein. This convexity is fun for a lot of different reasons. So now we have polygons. So first of all, we have the tropical set. The tropical set, as we said, U-trop, this is what generalizes, this is generalizing the lattice of co-characters of a torus. And now we have polygons in here. Maybe bounded, maybe not. Well, what do you do in toric geometry when you have a polygon? You have a way of defining a polarized toric variety. You have a partial compactification of a torus. We can get the same thing here. So let's say I have F is min convex. I can use this to define, from this I can define a graded version of my ring. I can define some A tilde living in A adjoint T, just a polynomial ring over my algebra A. This is going to be graded. It's exactly like, the construction is exactly like the graded ring you write down from a lattice polygon. How many people know what I'm talking about? If I write down a polygon, you can write down a graded ring in toric geometry. Just raise your hand, let me see how many people don't know. So here's what I mean. I can just literally tell you what it is, but you do exactly the same thing if you just drew a lattice polygon and you wanted to write down what's the projective toric variety given by that. You get it by writing down a graded ring and taking its proj. What this has just basis, theta r t to the r basis, t to the s, where s is where r, where f of r is bigger than or equal to minus s. The multiplication rule shows, the multiplication rule that I wrote down, the structure constants, show just immediately that this is a subalgebra of A of t. A tilde is graded subalgebra, where the grading is just by t degree. That's what I mean by the grading. All the thetas all have just, those are, these guys, this is the homogeneous guy. These guys have degree 0. It's graded just by t. So then what you do is you take the, so now if I take proj of A tilde, inside of that, just by graded ring, easy graded ring stuff, is spec of the old algebra. This, remember, this was our mirror. This was our mirror family. Remember, this was the mirror. This was the mirror family. And now I'm saying if I draw this polygon, I compactify all the fibers simultaneously of the mirror family. This I usually call X. It comes with a boundary. Let's call that E. I get a pair here of this guy inside of this. So what I'm saying here is, just by kind of copying toric geometry, basically what's true in toric geometry is all about monomials. What our theta functions are is a generalization of monomials. And we're sort of generalizing all the stuff you can do in toric geometry. So I get this thing here. So what was I saying? So here we're saying that if I have a function f is a regular function on U, what do I get from it? This construction here gives me a partial minimal model v living inside this x, which I should have written as sort of x sub f, dependent on this f or on the polygon. So a regular function gives me a partial compactification of the mirror, v inside of x. We can also go, so f regular on U gives me a partial compactification of the mirror. We can also go kind of the other way. Suppose I take on this side, suppose I take a partial minimal model of U. So I take U inside of Y. The claim is I get a function on the mirror. And that's almost directly by definition. We'll draw a picture here. Here's supposed to be a picture of the boundary. Here's sort of U, and here's its boundary. Each component of the boundary, E, by definition of partial minimal model, E is an element of the tropical set of U. And that's the basis of functions. So I can send this to, then I have theta E by definition. That's an element of, that's one of my basis elements of A. So that's a function from the mirror to A1. And so if I want to, what should I do if I have a bunch of them? I can send it to, I should call it theta, but there are a lot of thetas. So let's call it W, and a lot of people call this potential function W. The potential function corresponding to this partial compactification of U is just the sum over all e's in the boundary of y, the components of theta e. So that's a function now on the other side. So just naturally, we get this correspond. Of course, it goes in the other direction too. So regular functions give me a partial compactification over here. A partial compactification on this side gives me a regular function on the mirror. And now let me go back to the first example that I gave, the kind of thing I did at the very beginning when I talked about functions on affine space. So in examples, cluster variety, in the kind of examples that people really care about, most of the time, it's not the cluster algebra that you really care about, or the cluster variety that you care about. It's some partial minimal model of it. So usually, often, if we have u and y is often more interesting. For example, we had the case, the motivating case where y was the group, was a semi-simple Lie group, and u was the open double Bruja. And I think it's safe to say most people in the world don't know or care about open double Bruja cells, but more people, maybe still a small number, care about semi-simple groups. So this is the thing we really care about. Functions on the group, that really matters. That's what we want. So recall how we did it. So here we have a basis, the canonical basis, BU. What is it? It's the tropical sets of the mirror again. So that's U trop. And what's our candidate for y? By is just those functions on U, those canonical functions on U that happen to extend. In notation, that's BU intersect OY as a subset of OU. Intersect as a subset of OU, yeah. And our conjecture is that BY is a basis, always, of H0Y OY. We've proven it in dimension 2, and we've proven it in some cluster cases. We haven't proven this in full generality. We prove it basically in cluster cases when the compactification, in the cluster world, this kind of thing often comes by what are called frozen variables. You'll have this will be said, people say this is a cluster variety with frozen variables. The actual tori is the locus where the frozen variables are non-zero. So that's the situation. So then those cases are the cases where we were able to prove it. Here I just want to point out, in a really cool way, this set. So what should this be? So this is, roughly speaking, BU is like a lattice. That's our generalization of lattice. This is a cone living in the lattice. The claim is, the conjecture is, and we can almost prove this, always, that BY is exactly, it's cut out canonically, it's a canonical cone. In fact, the claim is that BY is, you take the potential function, you tropicalize it, so that gives us a cone. The claim is it's just this, inside of BU, which is the mirror. I call that V trop. So let's see why this is true. So the claim is that if you do this procedure kind of blindly, so we have this partial compactification that gives me a function on the mirror. I tropicalize it. That gives me a cone. I look at the lattice points in the cone, and the claim is that those are the functions on the thing I partially compactified. Let's see how that works. It works just kind of by formalism. So what is this? This is the set of V. V is the mirror, such that what's the condition? Well, it's that V applied to W is non-negative. Remember what W was. It was a sum of theta functions, one for each boundary component. We're still in the context of that little picture over there. So what is this? This is the set of V such that V of each theta E is positive. And now, come to a very appealing conjecture that I think is cool. So notice there are two pairings that we could write down on, if we take the tropical set for U and the tropical set for V, there are two natural pairings to Z. Take U and V. What could I do? Well, what does U do for me? U gives me a theta function on V. And what's V? Well, V is a point of the tropical set of V. That means this is a valuation on functions on V. Or this is a boundary divisor to V, to the variety V. So what could I do? the natural thing to do is to take v of theta u. Take the valuation, take this valuation and apply it to the canonical function given by u. That's one thing I could do. So, in other words, v is a divisor. That's sort of like take v corresponds to a boundary divisor. Let's say e sub v of this theta u. Of course, what could I also do just as well? I could do it in the opposite order. I could think of v as giving me a function on u. Take ov and then take u and apply to that. The conjecture is that these are the same. So the conjecture, these are the same. Call this the symmetry conjecture. That this pairing is symmetric. I have to say I don't know a good mirror symmetric reason why this thing should be true. And we cannot prove it in general. In dimension 2, it's true in dimension 2. Dimension 2 was proven in his thesis by Travis Mandel, who's here, by a really clever, short, easy argument. And we can prove it. The same cluster cases where we can prove this, we can prove it. So we have this also in some cluster cases. I think this is really a cool conjecture. But when you look at this in terms of theta functions, this is one situation where you look at our definition as theta functions, it looks pretty crazy. But I bet it's true. So assume it is true. Then what can I do with it? Then let's go back to what I was doing here. So I'm writing down, what are the points of this cone? Well, they're this, so let's rewrite this now. So now these are the v's such that the ord along E of theta v is positive. What's that? That just means I'm taking those functions theta v, those are functions on U that have no poles along any boundary divisor. That's just exactly by. That's just by. Do you see what I'm saying? That's just, these are the theta functions, those are functions on U. We're saying they don't have any poles on the boundary. It means they extend to the compactification. So it's just, so this statement is just kind of God-given that this is going to be true. Let me push this. I'm not a super good judge of what's going on with other people, but I do think I recognize boredom and dislike. So let me try to get you a little more pumped up. You may. Yeah. Yeah. I know almost nothing about representation theory. So let's talk later, like to Geis, and see what the answer is. I'm not sure about that.
I think the theta functions commute. They commute with decomposition and they commute with the torus action on G. So anytime the weight space is one-dimensional, the theta function will be a multiple.
Yeah, I'm going to say exactly. Let's jack this up to give some fun examples. Let's jack this up a little bit. So here I had U sitting inside of Y, and let's suppose I have more. Let's suppose I have a torus that acts on this picture. So I have a torus acting on Y, preserving U. Suppose I add that to my picture, to everything else. The claim is immediately I will get a map. I won't take the time to explain exactly why, but one part of this you'll see. I get a map then from V to the dual torus. The mirror gets a map to the dual torus. I'll call that the weight, because let's tropicalize this now. I get a map from the tropical set of V to the tropical set of a torus. That's its co-character lattice. This is the dual torus, so that's the characters of T. And I can say what this map is. If I take a V in here, associated with V I have a function on U, theta V. It's canonical. If you have a canonical function, it has to be preserved up to scaling by every automorphism, every continuous group of automorphisms. So this is automatically a T eigenfunction. So what must this map do? It must take T to the corresponding character. So this takes V to the weight, the T weight of theta V. So I get a map like that. And then I also have another map to A1 that was the potential function for U in terms of Y. So now I can write down, if I take an L in here, I can write down, I had a cone already, now I can write down a polytope. So I have a convex polytope. I take the weight, the little weight, inverse of L, and I intersect it with this big cone. The tropicalization of the potential function. So this now is a convex polytope. And what's it a basis of? This is living in By. This is a basis of, well, this was a basis of H0, O. What's this got to be? It's exactly the basis of this weight space. T acts on this by assumption. So I'm picking out the weight space. So I get a little polygon picking out the weight space. All right, so now let me give you an application of this. So what's the kind of example of this? This kind of picture is kind of a super basic thing in algebraic geometry. So let me give you an example of this. So an example of how you would do this. So let's start with a smooth projective variety. Smooth projective. And let's pick a divisor D, an anti-canonical divisor in here as we've been doing, with normal crossings and a zero stratum. And let's let U prime be the complement. And let's assume D supports ample. For example, you could assume that this guy is a Fano variety. Take the complement of an anti-canonical divisor on a Fano variety. And this, in algebraic geometry, people maybe don't get super excited about the fact that I claim I have a canonical basis of functions, because usually you study projective varieties, they don't have any functions. But here's a way to get functions. So let's let y over y prime be the so-called universal torsor. So this is a bundle, a torus bundle over here with for the group pick y prime dual. It's a principal bundle for the torus. So this torus acts on this guy with base this guy. The reason people care about this is the functions on y it's what's called the Cox ring of y. It's the direct sum over all line bundles on the original variety of their sections. It's a trick for turning sections of a line bundle into functions. Y prime L. And of course, this torus, this is just the weight decomposition for this torus. This torus acts. These are the characters of this torus. This is the weight decomposition. So you get this guy. And then let's just take U to be the inverse image of it. So this is an affine log Calabi-Yau almost by definition. This is a torus bundle over it. So this is again affine log Calabi-Yau. Affine log Calabi-Yau. And this is a partial minimal model for it, just because this is. Let me mention that this is the most important ring in birational geometry. Sort of all the everything about flips, flops, all that stuff, everything in Mori theory is about this ring. Like the strongest statement you can make in Mori theory is that this ring is, for example, finitely generated. So just like in representation theory, people their favorite thing would have been to have a basis of functions on a group. Mori theory, an unbelievable thing would be have a canonical basis of the Cox ring. Then sort of all of Mori theory would take place in canonical coordinates. Sort of, you could usually write down coordinates to study it. There'd be a distinguished set of coordinates to study. But we get exactly that. So we get a basis for this because this is our construction. So we get a basis of, so we have this By, a canonical basis. That would be conjecturally. So that would be, this would be in general, part of our general conjecture would, in this situation, give you a basis for the Cox ring. Both a canonical basis of every line bundle, and it's really the ring structure of the Cox ring that matters. That's what controls the flips and flops. We were describing the ring structure by these structure constants counting holomorphic disks. So we'd say that these disks sort of run all of Mori theory. It'd be what this. Yeah, let's say that this is a Fano, for example. It's a little more delicate to define this. You can do it, but it's a little bit more delicate. Say it's Fano, then there's no torsion. Or say it's, yeah. So this thing has a canonical basis, and let's see how it's cut out. Let's see what it looks like. Let's just apply the example I just talked about to this case. What do we get? So just apply the general machine in this instance. What do I get? So let's take the mirror. So we have V. So what do we get? We get V, which is the mirror to U. It maps to the dual torus. That's T pick Y. Well, this, if you remember our first conjecture, this is just the mirror family to U to start with. That was a family over T pick Y. This is just that family. So this is just the universal, the mirror to this piece of the universal torsor is the total space of the universal family of the mirror. So we get this. So this is the weight function in this case. We also get the superpotential W. for u sitting inside of y to A1. And now when I tropicalize, just do exactly what we were doing up there. Let's define this Q, L. So now take, at the tropical level, I have V trop going to pick Y and then a map to R by this W trop. Take a line bundle L in here. That was my little l before. This is the weight function. And define the polytope Q sub L. That's a subset now of BU, BU, which is V trop. So this is a convex polytope inside a lattice, always in quotes. It's absolutely canonical convex polytope inside the lattice. Its integer points parameterize a canonical basis of H0 YL. So we get in the canonical way, we get a polygon, we get a single cone. We get this single cone, which is the W trop greater than or equal to 0. That's a cone. And every time I fix a weight, I get a slice of that cone that gives me a polytope. Those polytopes, the integer points of the polytopes, parameterize the canonical basis of the sections of the line bundle. So this is just like the toric case. In toric geometry, a line bundle is the same thing as a polygon. Here we're generalizing it to the non-toric case. So let me give you a fun example of this. Maybe the really fun example from representation theory. So what choice did we have to make here? We have to make one choice. Given this Fano, I have to choose once and for all a boundary, an anti-canonical divisor, and then we get all this structure. Here's a really fun example where there's a canonical such choice. So here's an example. So let's take B. So we take a group G, and B is the full flag manifold, full flags. And let's take B cross B. That's a Fano variety. B cross B mod G, acting diagonally. This is a thing that Fox and Goncharov love. They call it comp 3 of B. This is again a Fano. You could ask, what do I mean by mod G? Take, for example, the symmetric GIT quotient. So take this as our Y prime. And a really cool thing, the reason they like this is this comes with an absolutely, so what, everybody knows what a flag is. These are just 3 flags. Take the SLN case, just three full flags. There's a completely canonical divisor in here, choice for this divisor D prime. It's anti-canonical on this Fano, and it's God-given. What's the choice? This is just the locus where the flags are not in general position. So you've got 2 flags. It makes everyone here themselves be able to come up with what does it mean for 2 flags to be in general position with respect to each other. That gives you, this divisor has 3 components on here. It's got one component coming from these two, and then these 2. So you get these 3 divisors. You add them up. The amazing thing is that they live in the anti-canonical class. So this is this guy, and so now I have a canonical choice for U prime is the complement. So this is my Y prime. I have the complement. Why do people like this thing? Let's keep going with this example. What's the universal torsor in this case? I'm just specializing the example that I just did. So here I have Y prime, which was this B cross B cross B triples of flags. What's its universal torsor? That's A cross A cross A, what people in representation theory called the base affine space. This is if H is a maximal torus, this is T pick Y prime is just H cubed. So this is a H cubed bundle. H cubed bundle. And why do people like A? What's true about H0 of A, that's the people like that because that's the direct sum over all irreducible representations of the irreducible representation. G acts on A. So the way it acts on its functions, you just get the direct sum of all irreducible representations. So this is the thing people would like to have a basis of. We get it by the same token. But a really fun thing here is I'm not making any choice at all. I've got this y over y prime, and I've got this d prime. And so what do I get out of this yoga? In this case, so let's pick of y prime. It's just, what's an element of this? It's the same thing as three weights. Three weights, alpha, beta, gamma for H. And in just specializing the case I just talked about, so in this case, what you get is, so here, I'll get this convex polytope, Q, alpha, beta, gamma, take three weights. That's the same thing as three dominant weights in the representation language. Q, alpha, beta, gamma, and what are its integer points? This is a basis for, or parameterizes, a basis for the corresponding irreducible representations V alpha, V beta, V gamma, G. So in particular, the number of this is what's called, I don't know quite the notation, maybe alpha, beta, gamma. These are what are called the Littlewood-Richardson coefficients. Littlewood-Richardson. So here, this machine is just producing canonically for every three dominant weights a polygon, a quote polygon, polytope, whose number of integer points are the Littlewood-Richardson coefficients. Without representation theory. It's just, we don't use the group at all. We just use this volume form on U. So we get this thing. Now, let me just stress, what do I mean when I say quotes convex polytope? I hope everybody gets it. This doesn't live in a vector space. It lives in this tropical set. So what I mean by that is each choice of torus. So I should have mentioned, by Fock and Goncharov, this thing has a cluster structure. This is a cluster. So each torus, TL, inside of U, identifies this Q, alpha, beta, gamma, with an ordinary, with a polygon, with a polytope in L. It gives you a lattice polytope. And it'll be described by explicit linear equations by tropicalizing the superpotential. It just comes to you cut out by inequalities. When you change the seed, these polytopes change. Their combinatorics change. The number of vertices changes, the number of faces changes, but the set of integer points stays the same. A theorem of Tim McGee, who's here, a student of mine, is that with the right choice of seed, with the right choice of seed, the superpotential here, this W, U inside of Y, is identified with the superpotential of Fock-Goncharov, or maybe it's Goncharov-Shen. There's a really beautiful. They write down a beautiful function on the mirror to this. Just a completely canonical function in terms of three flags. They have a way of constructing a function. It turns out that function just comes out of it's the function you get from our machine without thinking about groups at all. Tim showed that they're the same. And that implies, by the work that they do here, they also then study that this polytope, when you take this one particular seed, this is the hive polytope of Knudsen tau. These famous, maybe 15 years ago, they came up with just astonishing thing. They came up with these inequalities describing lattice polytopes whose number of integer points were the Littlewood-Richardson rules. It looked like it was just a kind of bolt of genius how they came up with these things. But here, we get these things out of this procedure, and I want to say, we don't just get this one, we'll get infinitely many others. Every single seed will give you another bunch of things that are just as good. It does exactly the same thing. Yeah, let's quit here. Go ahead.
You phrased everything in terms of the potential, but my impression was that many different potentials could give the same, because you were just tropicalizing the potential, you were just getting the polytopes out of them. So like in toric geometry, you would consider not functions, but you would consider convex polytopes or fans or something. So I'm curious just why you were focusing on a function which has too much information.
Well, to be honest, mostly because there are a couple of people here who've written papers about doing this kind of thing, taking a potential function, tropicalizing it, looking at the lattice points, and doing this thing. I could just be taking the piecewise linear function. I could just be taking piecewise linear functions.
And is there, so you get this sort of totally convex subset. Is there some coherent definition of totally convex subset where you can throw away, where you don't have to worry whether or not there's a potential that tropicalizes to
no, I gave you the definition. It's defined in terms of broken lines. So it's a completely, what I'm saying is I think really I kind of feel like integer affine manifold, that's sort of thing people use in mirror symmetry. But the problem with it is these tropical sets, they don't have an integer affine manifold that's canonical. They don't have an SYZ fibration, and if they did, then the SYZ fibration gives you a thing. Like in the Berkovich world, you can get an affine structure that way. But that involves a choice. You change that, you get a new thing. What you really have is just this fixed piecewise linear thing with, I don't know exactly what structure it has, but one thing it has is this version of straight lines, these broken lines. So, I like to do stuff just using those lines. And that's where you get, that's the kind of convex we can get.
Just so this last thing, so these Knudsen-Tau polytopes, I assume they were kind of uniquely defined, but your stuff here that depends on choices. Right?
Oh yeah, exactly. Where's Tim or Lauren knows it? What exactly do you when you choose this correct seed? That means you do something like factor the. What do you do? Factor the longest word in the.
That's my own. There's earlier paper by Lauren can probably correct that things too. Sorry. There's this earlier paper by Bernstein, Polytopes, I think. Tensor product implicitly is the lattice point polytopes, and they give a recipe which works in any E type and for any choice of reduced word for the long word. But in general, it's a union of product of many polytopes, I think, not just one. And then Knudsen-Tau took sort of everyone's favorite reduced word for the long word in Sn. And if you don't agree with me, I can tell you what your favorite is. It's you move one all the way to the end, then two to its position, and so forth. And they rearranged that in a way which looked much more symmetrical than the BFC formulation. That's the high function.
Is there an analog in this one?
Yes. So in fact, they're actually there are infinitely many things they could have done. They could have factored it. So, and those factorizations correspond to certain of these tori. But in fact, there's infinitely many others that you could do. So I think the right thing is really this, it's really this polygon living in this tropical set. That's the intrinsic.
Can you point to the right? I mean, the one that Knudsen-Tau form, can you point to the?
The one, well, what I'm saying is, let me just be clear. For us, the data was just, was this y, which was a cubed mod g, and this open set U, which was the complement of this canonical divisor. That was the data that we use. So this is just this data. We sort of tropicalize this data, and we get a subset of the tropical set that is convex in our way. And its lattice points parameterize, the number of lattice points is the Littlewood-Richardson's. Yeah. Now to turn that into an ordinary, go ahead.
Right? You have to choose a TL to get an ordinary.
Yes.
Do you know which TL?
Oh, yeah, that's what I was saying. T. McGee proved that, Tim proved that if you take the right choice of seed, the right source of CL, which is the one given by the factorization he's talking about, then it becomes the Knudsen one. So.
I expect the answer is that your cluster variables are take one part of each of the three flags and wedge them together.
Is Tim here? I really have no idea.
Actually, there is a special coordinate defined by function function, which are antics, the same as you said. Then in that coordinate, potential and Knudsen-Tau's
So you said that superpotential just has to be any mean convex function on the zero top?
Well, when I used the superpotential, that was the function I was getting from a partial compactification like this. And, as Greg was pointing out, I wouldn't guess that that actually is exactly the right thing. I mean, I didn't put any coefficients in front of it. I think it's probably the right thing when this is a Fano and I throw away an anti-canonical divisor. We can just call it the potential function. That's just a procedure. But to get a polygon, that's a tropical thing. I just need a min convex. That has nothing to do with, I don't need any varieties or anything. I need to have a piecewise linear function on the tropical set, which has this convexity property with respect to broken lines. Now, the only way I know how to come up with such a thing is by tropicalizing a regular function on the variety. But, maybe there'd be another way of getting them. I think probably not. Travis, you can ask Travis. He did a lot of this in dimension 2. I think he sort of showed that no, there are no other ones.
So one thing that people are sort of expected to come out of some sort of theory like this is, so do your thing of choose a convex function in a polytope and choose a particular cluster torus. People sort of expected the cluster variety to degenerate to the toric variety.
Oh yeah, I just didn't. Yeah, absolutely, I didn't do it here. But I didn't space it here. But we get So that's actually easy. One thing that would have been clear from the way Paul described cluster varieties as a blow-up is you can always, each choice of seed gives you a canonical degeneration of a cluster variety, as a union of tori, just to a torus. And under that degeneration, our theta functions just turn into monomials. We can see that degeneration in two ways. One, just by kind of graded ring tricks, so Riesz constructions. But also, let me just say, you can also just see it even without our theory at all, which is one of the reasons I didn't really want to stress it, is that, how do you do this? Look at the thing that Paul was saying. You take a toric variety, like A2. These toric models for the cluster varieties are always, it's not a projective toric variety. It's a toric variety with one boundary divisor for each cluster variable. You blow up some number of points. And then you blow up, and then you throw away the strict transform of the boundary. Well, there's an obvious thing you can do here. Let the points move. You can move the points all the way to infinity. When you move them to infinity, then you're not blowing up anything, and you're just getting a torus.
I understand this non-compactified. But the last part of your talk was about compactification.
Well, yeah, but if what you can also have this guy here. What'll happen is if these points move to here, when you blow up, you just get, if you blow up at that point, you just get a toric variety. So that's exactly what you get. Lots of people have degenerated things like flag manifolds to toric varieties. We'll get all of those things here. Much more interesting is you should be able to take something like the Higgs moduli space, the character variety for a punctured Riemann surface with any group. That's a cluster variety by Fock and Goncharoff. It's affine, so it's definitely got convex polytopes in it. That will at one time compactify the space in a nice way. You're guaranteed to have log canonical boundary, and you'll get a degeneration of the character variety to a projective toric variety. Like Andy and I looked at this for whatever the cubic surface is, 4-punctured sphere with SL2, and it's really cool. With it, you get the compactification. That thing is an affine cubic surface, and you get the compactification which throws in 3 lines. I think that's cool. And there are lots of people in that world, like Carlos Simpson, wanted to find good compactifications of the character variety, with nice boundary. And this just produces them just for free. Enough?